Hello guys, back with another power electronic circuit. We're looking at the third DC-DC converter today, which is the buck boost. We're done with the boost and the buck, which can both step up and step down voltages respectively. So now it's time for the third one, the buck boost, which as its name suggests can both step up and step down the input voltage. And another speciality of this is that the output voltage is going to be of the opposite polarity of your input. So and the duty itself, so up to 50% duty, when you vary it, you're going to get, it's going to operate in buck mode, so your output voltage is going to be lesser than your input voltage. And when your duty goes above 50%, ideally of course, you're supposed to get a boosted voltage, so a greater voltage. And so say if you give 60% duty and say some input voltage of 5 volts, you're going to get somewhere around say 7 volts or so, but you're going to get negative 7 volts, because you can see this is plus minus, this is going to be plus and minus. And another thing you can clearly see here, the capacitor, which we always generally put the negative terminal of the capacitor to ground, that is the standard, but here you have to and you must connect the capacitor in this way. You have to put the negative terminal to the top here and the positive terminal down. Otherwise, you know, in the whenever the inductor discharges, this is going to be an electrolytic capacitor, so it is polarized. You try and charge it the other way and it's going to blow up. That's the only thing which is going to happen, so take care. This has to be in this particular format. And yeah, the diode also, it has to be in this. Generally the diode, normally we always say the diode is in this direction, but yeah, here it has to be in this opposite direction, because I won't get into the KVL and how it works, but just to say simply, when the switch turns on your MOSFET, your source is going to charge your inductor. This is going to be the loop. When the switch is off, your inductor wants current. By its nature, it wants current to flow in the same direction, which was this direction. So it's going to follow this. It's going to charge the capacitor through the diode. So you can clearly see this capacitor gets charged here, positive here, and the diode gets forward biased. So it has to be in this. And again, yeah, the capacitor is going to discharge to your load. So that's how this works. So now let's go to the circuit here. And another thing, the buck and boost, I think I did it in the discrete or the analog way, as they call it. I used the TL494, which was the PWM IC. So today we're going to try something different. We're going to be doing it the digital way or the microcontroller way. I have here the MSP430, which I think I have used in one of the previous videos. It's nice. This is a development board, MSP430 G2ET, I think, yeah, that's the name, that's the development board, and that houses this microcontroller, the G2553. It's a low power, the entire series is a low power microcontroller series. So yeah, this is going to be good for this application. And yeah, I'll just show you the code in a bit, but first yeah, let's just go to the code before the circuit. So yeah, this is CCS, I think I've showed it. This is the IDE of TI. We code the microcontroller here, and this is embedded C. You do assembly, but yeah, I mean, that's, I find personally to be a lot of work. So yeah, I just go with embedded C. I'm used to that. So I won't go into exactly the detail of the code because it is a little big. And but as such, the timer generation, the PWM isn't the why the code is big, actually is because of this. This is the another thing, a new thing we're trying out today. This is basically this is not a pot, this is a encoder, a digital encoder. And yeah, I have posted a video on this before, I think, or I may not have. So yeah, basically pots have a maximum limit, as in you can turn it max on the right side, one maximum resistance, and other side maybe minimum. But encoders are basically digital, they work on digital pulses. They're not like potentiometers, which are analog. And encoders do not have an end, they go on limitlessly. So whatever way you program it in the microcontroller, you can basically handle it more cleanly. You know, there's no sway. Potentiometer, after all being a variable resistor, it's going to have some sway, it's going to be affected by temperature and such. So yeah, this is nice. And you just have to, once you have a module code ready for this, it's very nice, it's a dependable module. So yeah, I think it's just yeah, it has 5 pins. You give it 5 volts and ground from the board itself, and it gives you 2 outputs, clock and DT. And yeah, you handle that in the code. I won't go into the encoder. You can just look at the data sheet for that. So yeah, the code is here, and for every single rotation there's tactile feedback here, haptic feedback, yeah, that's what it's called. So every time you do click click click, you get a feedback. So every single turn I have mapped it to increase, and this is to control the duty. That is what this is for. What we were again doing in the TL494 with the pot, we're just replicating it with the encoder here. So every single turn I've given the lookup table here to be a change of 2.5% duty, which is good resolution. And main thing is with encoder you can vary it. You want it to be even more precise, say 1%, change the lookup table. You want to increase it, you want to make it 5% or 10%, change the lookup table, so that we have that flexibility here. So yeah, that is here. I have set up the timer, and the rest of the functions are mainly for reading the encoder, tracking where it is right now. So yeah, just scroll down the code here. There's a switch case in there. So yeah, the main here, I am taking the input of the encoders here, and this is what we're concerned with right now. I'm taking the output of the PWM here. So yeah, and the timer interrupts they have been used. So yeah, let's not go into the code right now. Let's go to the power circuit now. So yeah, Proteus, I put this in Proteus. Yeah, it's a good software. So yeah, another thing is we're talking microcontrollers and we're talking power. So one is low power, one is high power. We want to protect the low power side. Obviously we don't want anything to happen to our microcontroller, so we use optocouplers. And I have made a video on this before, so yeah, I'll just directly go into what we're doing here. We're giving that output of the square wave with variable duty to this here, to the input diode side, and the output, it's pulled up with 470. We're taking that output. And another thing is, this is inverted logic. When this goes high, basically when this gets forward biased, this is going to turn on and go low. So you have to handle that in your code. Just invert that, so whatever you want, you get it the correct polarity. So just handle that in the code. So after that, the output, this is basically the 6N137. I didn't mention that, which I'm using here. This is Vishays. This is a high-speed optocoupler, and here my switching frequency I've decided to be about 50 kilohertz. So yeah, we need a high-speed optocoupler here. If you use something like a 4N28, that's mainly for mains, rectification and all of that stuff, tracking that. So that's not suitable here. We need a high-speed one. So yeah, this is a good one. And yeah, this is the one which I'm going to be using, a single optocoupler. So it has the infrared LED and photo diode and the amplifier and all that inside that. So yeah, this is what I'm going to be using here. The output of that, I'm giving it to the IR2110, which we have used before. And that is, as you all know, it's of course because this is on the high side, it's not on the low side. And yeah, we need to drive the gate strong. We need to give proper, it has to handle the current. This optocoupler cannot handle that. That's again low power. So we need the driver here. So yeah, I've given that to the high side input. And since this is a logic level optocoupler, you can't give 12 volts here directly and get your level shifted output. You can only give max 5 volts according to the data sheet. So I just have 12 volts here. I'm just using the classic 7805. I don't want to bother with another buck regulator or anything here. So 7805 gives a clean stable 5 volts linear regulator. So we'll just take that, and that's what I'm giving to the rails of my optocoupler as well as the VDD of the IR2110. And yeah, we have the bootstrap diode, bootstrap capacitor to get the floating supply. So, and the low side input and low side output, we're not concerned. So NC, those are NC, we're not going to do anything with them. But yeah, we definitely need the bootstrap because we need the floating supply. And basically the output of this is going to be our level shifted to our VCC, which is 12 volts. And generally to drive a MOSFET properly, into saturation or whatever you want to call it, fully on state with minimum on state resistance, we want to drive it at least 10 volts and above. That's standard for all power MOSFETs. So this is 12, which is good enough. So that output level shifted we're going to get here on H out. And another thing is that is going to be with reference to this VS, which is the floating ground, you could call that, not with respect to ground, VS. So yeah, that is there. And now moving on to the final stage, this is our PWM is ready. Now the power circuit, which is just the same buck boost, we're going to give that power power PWM out here to the gate of this MOSFET through a 10 ohm. And yeah, this gate resistor, there are guides on choosing it, but yeah, generally we, to reduce ringing and all of that, we give 10 ohm. You can increase it, decrease it depending on how your waveform looks, but 10 ohm worked for me, so I'm just doing that. And here you can see I've put a 12 volt battery. It's not actually a battery, it's that same 12 volt which I gave over here in the 7805. So I just it won't, I didn't want to put this label here, the 12 volt one, but yeah, it's the same, it's not a separate battery, it's the same 12 volts. So we're giving that to the drain. The source is connected to the floating supply as well as the inductor and the cathode of the diode here. That diode is the 1N5819. It's a Schottky diode. A Schottky is good, it's low forward voltage drop and suitable for higher frequencies, which is exactly what we're doing here. And the 47 microfarad capacitor and a 100 ohm load. So yeah, you can decrease the load in case depending on what you want, but 100 ohm is fine for me right now. That draws a decent amount of current. So yeah, that is the circuit. Is now that the circuit is out of the way, overall, yeah, this is the circuit. I explained, I think, all of the parts. So yeah, optocoupler, driver and power, and yeah, the regulator. So now let's just go to the demo. So now that we're done with the schematic, I am now onto the circuit here, the physical circuit, and yeah, everything is on a breadboard again. And yeah, I know that's not super good because of the parasitics, and breadboards are generally meant for analog and lower power stuff, not of course not for this. But yeah, I mean, I didn't really have the time to sit and solder it on a perf board or something. So for now we're gonna have to make do with this. But yeah, of course a PCB layout or a perf board would have been better. But yeah, nevertheless, let's go into the circuit here. As I said before, the MSP board here, we have the encoder to vary the output, and yeah, that is going here to the optocoupler. This is our PWM output wire. This is the ground of the microcontroller, and you can clearly see it's isolated from this entire circuit here, which is important. There's no electrical conduction path between these, it's optically isolated, and that's exactly why we're using this optocoupler here. So after that, here we have the 7805, as I said, for the logic rails. And yeah, this is the IR2110, the driver, the bootstrap capacitors and all are in there to get the high side output. And yeah, I've just pulled out the high side PWM and the VS, which is our floating ground here. And after that, this breadboard is done, and that goes onto here, this small breadboard. We have the MOSFET here, the power MOSFET IRF-Z44N, which is a nice good classic MOSFET. And then we have the gate resistor here, and the 47 microfarad. Here I'm using a 400 volt one, which is probably why it looks so big, but of course you don't need such a big voltage unless you're working with that. But clearly we're not working with high voltage here, but I do not have another 47 microfarad lying around. So yeah, I should probably pick up one of the 35 volt or 50 volt ones, but yeah, that's for another time. But yeah, we can use that right now. And yeah, the diode we have here, the Schottky diode. And the inductor again, since it's a breadboard, it probably wouldn't fit into the leads here, it'll damage them. So I just use crocodile cables. And yeah, we have a toroidal inductor here of 200 microhenry. And finally, another the resistive load here, the power resistor we definitely need here. Don't use the 1/4 watt or 1 watt ones, it's not going to be enough. It's just going to burn up because this draws a decent amount of current. So yeah, this is a 10 watt rated one, so it should be good enough. And yeah, that is the basic circuit here. So let me just turn it on here, and yeah, we're going to see the PWM output on the oscilloscope and the output voltage here. I'll switch on the light. Currently it's at 0% duty, so let's turn the encoder. And yeah, as soon as I turn it right, 2.5%, and we can see here the output voltage has started coming. And yeah, let's keep increasing it by 2.5%, and clearly you can see the output voltage has started to increase, but we are still in the buck mode. And yeah, let's push say 50%. That's where we'll start seeing the difference. So moving this a bit at 30, I think it's a bit blurred, but yeah, at roughly 40% we have 8.4. And yeah, still pushing further. Now we are at 10.38, And officially the supply, it says 12 volts, but it's actually around 11, or not 11, I think it's 10.5. Yeah, it varies from time to time. But yeah, now we have entered into the boost region after this point here, 13.1. And yeah, we do not, another thing is, be careful, don't push it too close to 100%, because the core of the inductor will get saturated and it's practically a short, so it would damage and burn everything. So yeah, let's not push it too high, but 13.6, I think it reached that. So yeah, we can stop it at that. That's good enough. And the resistor is starting to heat up too, but it's all safe because it's 10 watts. So yeah, we clearly saw here, and the even the waveform has started jumping a bit, probably because of the parasitic and all of that. But yeah, no worries. The output voltage is stable, and the resistor, yeah, it's drawing current, and clearly we saw that it both bucked and boosted the output, and the output voltage is negative. The polarity is there. So yeah, this demo was to demonstrate this exact thing. And we use the microcontroller, which is another nice touch, and the encoder. So that was a good thing, and of course isolation important. So many blocks got covered today, and yeah, this circuit turned out to be a success. So just switched it off. But yeah, good circuit. Do try it out. Good learning. Mix of embedded and power is always nice. Meeting two worlds, that's always good, mixing them. So yeah, I hope today's circuit was good. And yeah, I'll keep posting these videos. It'll be good for me to track my progress, and also if somebody watches this and learns something, that's always a good plus. So yeah, thank you for this. Bye guys.